An extraordinary event transpired near perihelion between October 29th and October 30th. As 3I Atlas momentarily vanished from our view behind the Sun, orbiting spacecraft registered an astonishing sight. The celestial body appeared a deeper blue than the Sun itself, surpassing even the radiant intensity of a star 5,800 degrees Celsius. Furthermore, it underwent an inexplicable acceleration of 135 kilometers per day squared, propelled by a force with no discernible origin. During this critical period, NASA observations were obscured by a governmental shutdown, and vital imagery from Mars, potentially holding answers, became inaccessible due to bureaucratic delays. A scientific assessment indicated that if this phenomenon were purely natural, a significant gas cloud, comprising 10% of the comet's mass ejected into space, should be observable in December. The absence of such a cloud, or the failure of this prediction, would signify an object defying all current scientific models. 9 documented anomalies, 9 unexplained characteristics within a single entity have been observed. Concurrently, the broader scientific community is engaged in debate over the fundamental question of whether this object might not be a comet at all. December 19th marks the date of 3 Atlas's closest approach to Earth, a moment when every major telescope will be directed towards this interstellar visitor, finally revealing its true nature. However, the data already gathered today is demonstrably challenging established scientific principles. To remain informed about what may be the most significant astronomical discovery of this decade, please engage with this video by liking it and subscribing to our channel. Share your location and current time in the comments, and express your thoughts on whether 3 Atlas is merely an unusual comet or something more. To contribute to the expansion of our community and ensure wider awareness of the ongoing developments surrounding 3 Atlas, please share this video on social media platforms and activate the notification bell to receive timely updates as December draws nearer. Your support is invaluable. Thank you. The impossible blue shift. Let me elucidate why this specific hue holds such profound significance, elevating it beyond a mere astronomical curiosity. When we perceive color in the cosmos, we are observing the intricate interplay of chemistry and physics, the fundamental forces governing matter's interaction with energy. A crimson comet, for instance, signifies dust particles scattering sunlight, with carbon compounds absorbing certain light wavelengths while reflecting others. A verdant comet points to diatomic carbon molecules energized by ultraviolet radiation, fluorescing with the characteristic emerald glow observed in numerous comets within our solar system. However, a cerulean manifestation signifies something entirely different: emission, not merely reflection. It implies that something within or surrounding 3 Atlas is actively generating light across wavelengths that should not be predominant in the spectrum of an ice ball warmed by a distant star. As stated plainly in an analysis, dust particles are expected to rescatter sunlight, and the surface of 3 Atlas should be approximately 20 times colder than the Sun's photosphere, resulting in a predominantly reddish, not bluish, appearance. The object's bluer than the Sun coloration directly contradicts the fundamental thermodynamic principles governing the interaction of cold bodies with stellar radiation. The comet's evolving color itself narrates a perplexing story. Merely months ago, in July and August, 3 Atlas presented a reddish hue, a typical signature of a dusty, carbon-rich body illuminated by solar radiation, as evidenced by deep-field telescope imagery. Subsequently, in September, during a total lunar eclipse, amateur astrophotographers Michael Jagger and Gerald Riemann captured breathtaking images from Namibia, revealing a shift to a greenish color, a classic emission from diatomic carbon molecules excited by ultraviolet radiation, characteristic of comets venturing into the inner solar system. Now it is an intensely, impossibly blue. The implications of this color transformation are profoundly concerning to leading astronomical minds. When we observe color in the expanse of space, we are essentially deciphering chemistry and physics, the foundational mechanisms dictating the relationship between matter and energy. A red comet indicates the presence of dust particles reflecting sunlight and carbon compounds, absorbing and reflecting specific wavelengths. A green comet suggests diatomic carbon molecules reacting to ultraviolet radiation, emitting the characteristic emerald luminescence seen in many solar system comets. Yet, blue signifies something distinct: emission rather than mere reflection. It implies that elements within or surrounding 3I Atlas are producing light at wavelengths incompatible with a frozen ice ball subjected to distant stellar warmth. One analysis explicitly states that scattered sunlight from dust is anticipated, and the surface of 3I Atlas should be approximately 20 times cooler than the Sun's photosphere, leading to a redder hue, not a bluer one. For this celestial body to appear bluer than the Sun defies the established thermodynamics of how frigid objects interact with stellar illumination. The data collected originates from multiple independent sources, precluding dismissal as an instrumental error or observational anomaly. Stereo A's dual cameras, specifically the HI-1 and Core 2 instruments, both documented the blue shift. SOHO's LASCO C3 coronagraph corroborated these findings. GOES-19, a weather satellite coincidentally monitoring solar activity during the crucial period when 3 Atlas was obscured from Earth's view by the Sun, captured the identical, extraordinary azure luminescence. These instruments, developed by disparate teams and operated by different agencies, processed through distinct data analysis pipelines, collectively observed the same phenomenon: light emission, not passive reflection. This distinction is paramount, separating a minor anomaly from a profound enigma. When sunlight interacts with dust or ice, it scatters and reflects, with the perceived color being the surviving wavelengths after absorption by the material. Emission, however, is fundamentally different. It signifies a source actively glowing, releasing energy in the form of photons. This indicates that elements within or around 3I Atlas possess sufficient heat, energy, or an unusual characteristic to generate blue light that overwhelms the expected reflected sunlight. The most immediate scientific explanation posited is ionized gas. When molecules within a cometary coma are struck by solar ultraviolet radiation, electrons ascend to higher energy states and, upon returning to their ground state, emit photons. Different molecules produce different colors. Carbon compounds, under specific conditions, can emit blue light. It is conceivable that 3 Atlas possesses an exceptionally unusual composition, with a high concentration of volatile carbon species, generating this blue emission through straightforward photochemistry. However, this hypothesis is challenged by existing spectroscopic data. Spectroscopic analyses from August 24th, obtained from the KEK telescope, and from August 25th, acquired by the Very Large Telescope, revealed a peculiar characteristic. 3 Atlas exhibits an unusually low abundance of carbon chain molecules, specifically C2, which typically imparts a green glow to comets, and C3, contributing to their overall color signature. The ratio of cyanogen to carbon chains is among the highest ever recorded for any comet. A publication by Luis Salazar Manzano from the University of Michigan unequivocally states that 3 Atlas is among the comet's most depleted in carbon chain molecules. Therefore, if it lacks the molecules responsible for typical colored emissions, what is causing its blue luminescence? This juncture introduces speculation, blurring the lines between conventional scientific understanding and unsettling inquiries. Some researchers propose that the blue emission could originate from carbon monoxide molecules undergoing ionization at exceptionally high rates, resulting in a blue fluorescence of unprecedented intensity. Others draw attention to the peculiar nickel signature, the enigmatic emission of nickel without iron, which has been a persistent anomaly associated with 3 Atlas. Could nickel compounds, energized by solar radiation, contribute to this blue glow? It is known that nickel tetracarbonyl dissociates under ultraviolet light, releasing both nickel atoms and carbon monoxide. It is plausible that some exotic chemical reactions involving these dissociation products are responsible. However, Lowe's analysis ventures further, presenting a possibility that many colleagues may find uncomfortable. He questions whether the blue color is intrinsically linked to chemistry at all, proposing instead a role for active heat, not merely the passive warmth of solar radiation, but internal heat emanating from a non-solar source. He observed that for 3 Atlas to appear bluer than the Sun, its emission spectrum must either be hotter than the Sun's photosphere or operate via a mechanism that preferentially generates blue light. The implication, though not explicitly stated, suggests the potential for an internal power source, explaining both the blue color and the concurrent rapid brightening. An artificial construct with an engine, operational systems generating waste heat, and emission profiles unrelated to natural cometary processes would indeed manifest in precisely this manner. Before dismissing this as mere science fiction cloaked in academic discourse, consider the known facts versus our assumptions. We have documented 9 anomalies associated with 3 Atlas: its orbital alignment within 5 degrees of the ecliptic plane, its anti-tail pointing towards the Sun, its extreme velocity, its massive nucleus, its early onset of outgassing beyond Jupiter's orbit, its unique nickel without iron signature, its dominant carbon dioxide presence, its precisely tuned trajectory, and now its striking blue coloration. Individually, each anomaly could be attributed to chance occurrences, unusual compositions, or the inherent diversity of nature. However, the confluence of 9 anomalies, 9 deviations from expected behavior in a single object, raises serious questions about statistical improbability. At this point, one must contemplate whether we are observing an exceptionally peculiar comet or something entirely different. The color alteration occurred precisely during the period when 3 Atlas was unobservable from Earth, a consequence of celestial geometry rather than a deliberate concealment. As the comet traversed the far side of the Sun, it entered solar conjunction from our vantage point, its proximity to the Sun's glare rendering it invisible to ground-based telescopes. During these crucial days, when it should have been at its most active, with solar heating driving peak outgassing and providing an opportunity to ascertain its composition and behavior, it was hidden behind our star. The only instruments capable of observing it were space-based solar observatories fortuitously positioned to capture the event. Some interpret this timing as suspicious, suggesting an object with a trajectory meticulously designed to pass near Mars, Venus, and Jupiter, while remaining hidden from Earth during its most revealing phase, appears almost intentionally engineered to thwart observation. Conversely, others argue this perspective is anthropocentric, asserting that the universe operates without regard for our observational angles, and our current geometry is simply a matter of unfortunate coincidence. Both viewpoints are rational and equally unprovable. However, the timing is undeniably frustrating. The subsequent events are of paramount importance. 3I Atlas is expected to re-emerge from behind the Sun in mid-November, becoming visible again around the 11th in the pre-dawn sky, low in the constellation Virgo. Amateur astronomers equipped with telescopes of 8 inches or larger should be able to detect it as a faint, fuzzy patch against the background stars. Its visibility, however, is unlikely to remain diminished for long. If the brightening trend observed at perihelion persists and the object continues to defy predictions, It could appear significantly brighter than the estimated magnitude of 12 to 13. More critically, its color will be a key indicator. It may remain blue, transition to another color, revert to red, or exhibit an entirely unforeseen spectral signature. Each scenario offers a distinct insight into the true nature of 3 Atlas. A return to red would suggest the blue phase was transient, dictated by specific perihelion conditions that have since passed. Persistent blue coloration would indicate an ongoing emission process independent of solar proximity. A shift to yet another color, possibly back to the September green, would imply evolving complex chemistry as the comet recedes from the Sun. However, one scenario, though not publicly discussed, may weigh on some minds. What if 3 Atlas emerges from behind the Sun and is dark? What if the observed brightening was not the onset of increased activity, but its conclusion? What if an event, unseen by us at perihelion, fundamentally altered the object? Comets are known to fragment, to undergo outbursts expelling vast quantities of material before quieting down, and, on rare occasions, to disintegrate under the strain of solar heating. If 3I Atlas does not reappear as anticipated, or emerges dimmed or absent altogether, speculation will intensify. Some will propose fragmentation due to perihelion stresses exceeding its structural integrity. Others will reference the detected non-gravitational acceleration, the apparent thrust altering its trajectory, and question whether it maneuvered, changed course, or acted precisely as Lowe has cautioned it might. The approach to Earth on December 19th will provide definitive answers. As 3I Atlas nears our planet, reaching within 270 million kilometers, the Hubble, Webb, and numerous ground-based telescopes will focus their full observational power on this interstellar visitor. High-resolution data will finally be obtained, revealing its true color with precision. Spectral lines will be measured, identifying constituent molecules and their ratios, and confirming whether the blue glow persists, and if so, its cause. Until then, we are left with an anomalous observation and insufficient explanations, contemplating a comet that shines bluer than the sun it orbits. We are left to ponder whether we are witnessing exotic natural phenomena from an ancient star system, or something else entirely, something deliberately enigmatic. Acceleration without explanation. The figures originate from David Finoia at NASA's Jet Propulsion Laboratory, a navigation engineer holding a doctorate in mathematics from the University of Pisa. His professional career is dedicated to the meticulous calculation of trajectories with meter-level precision across vast interplanetary distances. Consequently, when Finoia submits a report detailing non-gravitational acceleration, it commands significant attention. When this report pertains to 3I Atlas, it prompts inquiries that defy straightforward answers. An acceleration of 135 kilometers per day squared was recorded in the radial component, pushing away from the sun. An additional 60 kilometers per day squared was observed in the transverse direction, perpendicular to the sun's path. These are not insignificant forces. They exceed instrumental uncertainties or statistical noise. This represents tangible, measurable directional thrust occurring at precisely 1.36 astronomical units from the sun at the very moment of perihelion when observation was impossible. Comets do exhibit acceleration. This must be clearly understood before speculation escalates. Every active comet in our solar system experiences non-gravitational forces as ice sublimates on its sunward side, generating gas jets that propel the nucleus, akin to a miniature rocket engine. This is termed the rocket effect and is considered normal. Darrell Seligman of Michigan State University has repeatedly emphasized this point since the report's release, noting that comets routinely display non-gravitational accelerations and that the absence of such would be peculiar. However, 3I Atlas deviates from this norm in several key aspects. the magnitude of its acceleration relative to observed outgassing, the timing of its occurrence, and most disturbingly, its implications regarding mass loss. Lowe conducted calculations that many others were considering but hesitant to publish. To achieve an acceleration of 135 kilometers per day, squared through the rocket effect, driven by typical gas ejection from a sublimating surface, necessitates substantial mass loss. Momentum conservation dictates that every kilogram of gas expelled at hundreds of meters per second imparts an equal and opposite momentum to the nucleus. For an object the size and estimated mass of 3I Atlas, generating such thrust implies a loss of approximately 10% of its total mass over a 1-month period. 10%. This is not a gentle dissipation of ice crystals. It represents catastrophic mass loss. It suggests the comet is effectively disintegrating, expelling billions of tons of material in a continuous, hurricane-like outgassing event that should generate a colossal, brilliant, and unmistakable cloud of gas and dust surrounding the nucleus. Such a cloud should be readily detectable across the solar system and by all telescopes when 3I Atlas becomes visible again. Lowe's prediction is unequivocal. A dense gas cloud should be observable in November and December. He states should, not might or could, because if the non-gravitational acceleration is a result of natural cometary outgassing, the laws of physics mandate the existence of that cloud. It is an unavoidable consequence, not a possibility. Momentum conservation is not a suggestion. It is a fundamental principle governing all interactions in the universe, from galactic collisions to the motion of billiard balls. Therefore, what are the implications if this cloud is not observed? This is the unspoken question that looms over every discussion of 3I Atlas, even if not articulated by the mainstream astronomical community. If December arrives and the Hubble, Webb, and ground-based arrays meticulously examine the object at its closest approach to Earth, and they observe a relatively modest coma, a typical tail, and outgassing rates consistent with a normal comet at that solar distance, then the rocket effect cannot account for the observed acceleration. The mathematical and physical models do not align. An alternative explanation must exist for the observed thrust. Lowe proposed a hypothesis, not as his preferred explanation, but as a necessary consideration given its potential ramifications. He suggests that the non-gravitational acceleration might represent the technological signature of an internal engine, using his exact published words from October 31st, the same day Fenoya's report was released. An internal engine, a propulsion system, a device engineered to alter velocity, trajectory, and maneuver. The immediate counterargument posits that a single data point does not establish a pattern. Non-gravitational acceleration has only been documented at perihelion. We lack tracking data demonstrating sustained thrust over extended periods, and evidence of course corrections beyond what natural forces can explain. We have one measurement taken at a single moment, during a phase where maximum cometary activity is anticipated. Formulating a groundbreaking hypothesis based on such sparse evidence is, at best, hasty, and at worst, reckless. Nevertheless, here lies the inconvenient truth. We would be incapable of detecting even a continuous, subtle propulsion if it were active. The object designated 3I Atlas is too distant, its velocity too great, and it is monitored by too few observatories to accurately gauge minute variations in its speed in real time. The sole reason Fenoya was able to ascertain the acceleration was the presence of perihelion, which provides a fixed point of reference. One can contrast the anticipated trajectory, calculated solely from gravitational influences, with its observed position post-perihelion and extrapolate backward to deduce any additional forces that must have been applied. Beyond this specific time frame, the uncertainties become too vast and observational gaps too frequent. This presents one of the most vexing challenges in the study of interstellar objects. They are fleeting visitors. By the time we detect them, mobilize our telescopes, coordinate observations, and commence data collection, they have already traversed a significant portion of the inner solar system. We are afforded a single opportunity, one pass. Should any event occur during the weeks or days when we are unable to monitor it, when it is obscured by the sun's glare, dips below the horizon, or becomes too faint to track, we miss it entirely. This leaves us with voids in our data, which speculation is quick to fill. Furthermore, the acceleration occurred at the ideal juncture for a maneuver. This detail, while sounding conspiratorial, is entirely understandable when one grasps orbital mechanics. Perihelion is precisely when a spacecraft would execute a gravity assist maneuver, leveraging the intense gravitational field near the Sun to maximize the effectiveness of any applied thrust. Igniting engines at perihelion while moving at peak velocity results in a far greater alteration of the final trajectory than activating those same engines at any other point in the orbit. This is fundamental physics, taught in every astronautics course and utilized by every mission planner aiming for efficient exploration of the outer solar system. If 3I Atlas were an artificial construct, a probe, a spacecraft, or any designation for a technological artifact from another civilization, perihelion would indeed be the anticipated moment and location for propulsive maneuvers. One would wait until hidden from Earth-based observation, until reaching the point of maximum gravitational assistance. Then engines would be fired when fuel expenditure is minimized and the trajectory change is maximized, all without external scrutiny. Naturally, this same logic applies in reverse. For a natural comet experiencing maximum solar heating, perihelion is precisely when one would expect the most significant outgassing, thereby producing a substantial rocket-like acceleration. The timing itself proves nothing. It aligns with both the mundane explanation and the extraordinary one. We are left in a state of unsettling ambiguity, aware that something occurred but unable to definitively identify its cause. There is also the matter of the acceleration's vector. An acceleration of 135 kilometers per day, squared directed radially outward, is consistent with a rocket effect. Gas expelling from the sunward side propels the comet away from the sun, as expected. However, an acceleration of 60 kilometers per day, squared transverse to the sun's direction, a lateral force, does not arise naturally from simple, uniform outgassing. This would necessitate asymmetric jets, active regions on the nucleus preferentially venting gas in specific directions, generating a net force coincidentally perpendicular to the sun's gravitational pull. Again, this is not impossible. Comet nuclei are not perfect spheres of uniform composition. They possess varied terrain, areas with more exposed ice, and regions where dust layers insulate the interior. Sunlight strikes these surfaces at different angles, causing some areas to sublimate more rapidly than others. The resulting gas jets are directed by the local topography. If a jet erupts from the evening terminator, the boundary between day and night on a rotating nucleus, it can produce precisely the transverse acceleration observed. However, this requires a very specific alignment of conditions. The active regions must be correctly positioned, the rotation must have the appropriate orientation, and the gas jets must exhibit precise strength ratios. It is plausible, but it demands a highly particular configuration of circumstances. Conversely, a propulsion system designed for velocity modification would naturally generate thrust vectors that are not aligned with the sun's direction. Engines are pointed towards the desired destination, not dictated by the sun's position. What makes this entire situation so exasperating is that we possess the technological capability to definitively answer these questions, yet we cannot deploy it in time. A close flyby mission, a dedicated spacecraft dispatched to intercept 3I Atlas, would resolve all ambiguities instantly. Cameras would provide direct imaging of the nucleus. Spectrometers would precisely measure its composition. Particle detectors would sample the coma, detailing precisely what is being ejected and at what rates. Within hours, we would ascertain whether the acceleration is attributable to natural outgassing or some other phenomenon. However, there was insufficient time to launch such a mission. 32 Atlas was detected on July 1st. Perihelion occurred on October 29th. 4 months is an inadequate time frame for the design, construction, testing, and launch of a spacecraft, let alone for it to reach its target. Mission proposals have been drafted, and engineering studies have been completed. Multiple teams have demonstrated the feasibility and affordability of intercepting future interstellar visitors. Yet, for Thur-second Atlas, we are confined to remote observation, viewing it from hundreds of millions of kilometers away and attempting to infer internal processes from faint photons collected by telescopes. The European Space Agency's JUICE spacecraft will offer some data when it conducts observations between November 2nd and November 25th. These instruments will capture through Atlas in the immediate aftermath of perihelion, during the period when significant outgassing should still be generating a substantial, detectable coma. However, the data will not reach Earth until February 2026, as the spacecraft is too distant and its data transmission rate too slow, compounded by a lengthy queue of scientific observations. We wait, we theorize, we ponder. Meanwhile, 32 Atlas proceeds on its trajectory, unseen and unmonitored as it arcs away from the Sun and back into the void from which it originated. If it is a comet, it is shedding mass, creating that debris trail, behaving precisely as natural processes dictate. If it is something else, if those 9 anomalies are not coincidences but indicators, it might be adjusting its course, altering its velocity, preparing for whatever lies ahead in a journey that began billions of years ago in a star system we may never witness. December 19th will reveal which of these possibilities is closer to the truth. Until then, we are left with 135 kilometers per day squared of thrust and no consensus regarding its origin. The missing Mars imagery. October 2nd, 2025. 3I Atlas passed within 30 million kilometers of Mars, a proximity closer than Mars has ever approached Earth in recorded human history. This proximity offered spacecraft orbiting the red planet their best opportunity to observe an interstellar visitor since humanity began placing instruments around other worlds. According to multiple sources, given the geometry of the flyby and the capabilities of the available instruments, one particular camera possessed an ideal vantage point. HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, is a camera capable of resolving features as small as 30 centimeters across from an altitude of 300 kilometers above the Martian surface. This instrument has photographed avalanches in mid-collapse, dust devils casting shadows, and the parachutes and landing platforms of rovers that touched down decades prior. When directed at an object 30 million kilometers away, it could achieve a pixel resolution of approximately 30 kilometers. While this may not sound impressive, it is important to recall that our most detailed images of Third Atlas from the Hubble and Keck telescopes had resolutions 3 times inferior. These images were indeed captured. Multiple researchers have confirmed that HiRISE was tasked with observing through Atlas during the Mars flyby window. The geometry was advantageous, the pointing feasible, and the observation executed. Subsequently, the images vanished into the bureaucratic void created by a government shutdown that commenced on October 1st and persisted for weeks. Avi Loeb has been explicit on this matter. In his appearance on the Joe Rogan Experience, in his written statements, and in numerous interviews with various news outlets, he has unequivocally stated that he requested access to those images. He communicated directly with the principal investigator of HiRISE. He received no response. He followed up, Still, nothing. The images exist, residing on a server within NASA's data pipeline, yet they have not been released, not made public, and not shared with the scientific community that eagerly awaits them. NASA has neither confirmed nor denied the existence of these images, maintaining a deafening silence. Now, before we delve into speculative territory, it is crucial to understand the actual events that transpired during that shutdown. On October 1st, the United States government's funding authorization expired. Various agencies, including NASA, were compelled to furlough non-essential personnel. Scientific operations continued where possible, but communication channels were disrupted. Press releases ceased, and data sharing slowed considerably. The public-facing infrastructure that typically ensures immediate availability of NASA observations went dark. This was not an unprecedented occurrence. Government shutdowns have happened before, invariably disrupting scientific endeavors. Observations are postponed, data releases are delayed, and the machinery of publicly funded research grinds to a halt, not due to any deliberate attempt to conceal information, but because the personnel responsible for processing and disseminating that data were at home, unpaid, awaiting a congressional budget resolution. This is institutional dysfunction, not deliberate obfuscation. However, the timing is what fuels public disquiet. Thirthang, Atlas made its closest approach to any planet during its entire transit through the solar system, the singular moment when high-resolution imagery could have been acquired from a perspective that will never be available again. At that precise juncture, the system responsible for sharing such imagery ceased operation. The coincidence feels almost deliberate, even though we understand it to be otherwise. We know the shutdown was unrelated to 3-3 Atlas. The budgetary deadlock stemmed from domestic policy and political maneuvering that had been escalating for months. Yet the timing, as Avi Loeb aptly described it, was a manifestation of terrestrial stupidity, not evidence of extraterrestrial involvement or a clandestine cover-up, but rather basic human incompetence impeding scientific discovery. The universe, he stated, does not pause for government shutdowns. Science does not halt because politicians cannot agree on spending bills. And when presented with a once-in-a-lifetime opportunity to observe an interstellar object at close range, forfeiting that chance due to bureaucratic paralysis is inexcusable. Florida Congresswoman Anna Paulina Luna apparently shares this sentiment. Reports indicate she has been actively working to secure the release of those high-resolution images, employing any available political leverage to urge NASA toward greater transparency. Whether this stems from genuine concern for scientific progress or opportunistic grandstanding remains unclear. What is significant is that an individual with actual authority is posing the same questions that astronomers have been asking since October. Where are the images? When will they be released? What are they waiting for? The European Space Agency did release images. ESA's Mars Express and ExoMars Trace Gas Orbiter both observed 3-2 Atlas during the October 1st through October 7th window. The ExoMars TGO image depicts the object as a faint, fuzzy point, barely distinguishable from background stars, captured while the spacecraft's camera was tracking the fast-moving target. Background stars appear as streaks, while the comet appears stationary. This is an impressive feat of pointing and tracking, yet it reveals virtually nothing about the object itself. No discernible nucleus, no detailed coma structure, merely confirmation that, yes, 30 Sandal Atlas was where predicted, and yes, it possessed a vaguely comet-like appearance from 30 million kilometers away. NASA's Mars rovers and the Mars Reconnaissance Orbiter were also slated to observe the flyby. NASA had confirmed this in advance. Curiosity, Perseverance, and MRO were all intended to capture images during the optimal window. Then the shutdown occurred, and the flow of information ceased. We do not know if Curiosity captured anything. We do not know if Perseverance directed its cameras skyward. We do not know what MRO recorded beyond the high-rise observations that purportedly exist but remain undisclosed. China's Tianwen-1 orbiter should also have had a view, with over 14,000 published images of Mars and its surroundings. The Chinese space program is not reticent about releasing spectacular data when available. However, there has been no statement from the China National Space Administration, no accompanying images, no press releases, and no indication that they observed through Atlas at all. Some have suggested that this silence is more concerning than NASA's, as it is voluntary rather than a consequence of a shutdown. If the images revealed something ordinary, something entirely consistent with a natural comet, why would China hesitate to publish them? Why would they forego an opportunity to showcase their observational capabilities? The explanation might be as straightforward as data processing delays. Space agencies routinely require weeks or months to calibrate and validate their observations before public release. Raw data directly from a spacecraft bears little resemblance to the polished images presented in press releases. Detectors exhibit noise, cameras have artifacts, and cosmic rays can generate spurious signals. Every frame must be meticulously checked, cleaned, and analyzed. The fact that we have not yet seen Chinese images does not necessarily imply any suspicious activity. It may simply indicate a thorough processing protocol. However, the absence of information creates a void that speculation readily fills. Reddit threads dissect the timeline. YouTube videos draw connections between the shutdown, the missing images, and Avi Loeb's warnings about 3 Atlas. TikTok explainers assert that the object went dark, altered its course, or is somehow being deliberately concealed from public view through coordinated governmental action. None of this is substantiated by evidence. All of it is unfalsifiable because the data that would resolve the question remains unreleased. This is the frustrating reality of conducting scientific research in the modern era when the subjects of study also captivate intense public interest. Transparency is expected, even demanded, when data does not appear promptly or when there are gaps in the information flow. People tend to assume the worst: cover-ups, conspiracies, and deliberate obfuscation. Sometimes they are correct. More often they are mistaken. But without the data, without the images, without confirmation that, yes, this is what 3 Atlas appeared like from Mars orbit on October 2nd, we cannot differentiate reasonable skepticism from paranoid fantasy. What would those high-rise images actually reveal? If they exist and are eventually released, what would we learn? The resolution is sufficient to potentially observe the nucleus directly and measure its size with genuine precision, rather than relying on broad uncertainty ranges that currently place its diameter anywhere between 440 meters and 5.6 kilometers. We would observe the coma's structure, the distribution of gas and dust surrounding the nucleus, noting whether it is symmetrical or exhibits jets and active regions. We would acquire color data that could aid in identifying the composition of the ejected material. Most importantly, we would ascertain whether the object appears normal, whether it possesses the diffuse, irregular, unequivocally icy appearance characteristic of every comet we have ever examined up close, or if it exhibits sharp edges, geometric features, and surfaces that reflect light in ways inconsistent with ice and rock. At that distance, high-rise would not resolve minute details, but it could distinguish between a natural body and an artificial one. It could provide a definitive answer to the question that Avi Loeb repeatedly raises, and that most scientists tend to dismiss. The fact that we still lack those answers is maddening. The fact that the images are stored somewhere in a database, already captured and transmitted to Earth, yet inaccessible due to political discord, bureaucratic caution, or simple neglect, is almost more disheartening than if the observations had never been attempted. We were so close. 30 million kilometers is an insignificant distance in astronomical terms. We possessed the instruments, the opportunity, and we allowed it to slip through our grasp. Avi Loeb frames this as a failure of scientific culture. We are too reactive, he contends, too inclined to wait and observe rather than preparing proactively. 30 Atlas was discovered in July. By late July, it was evident that the object would make a close approach to Mars in October. Months were available to coordinate observations, ensuring that every available instrument was trained on the target and that data would flow unimpeded, irrespective of political circumstances. Instead, we relied on standard procedures, assuming that everything would function as it invariably does. When it did not, we lost data that can never be recovered. The shutdown concluded, NASA resumed operations, and the data archive was quietly reinstated. However, there has been no announcement regarding the high-rise images, no statement about when or if they will be released, and no explanation for the communication lapse. This episode has fostered a lingering distrust, a sense that even if no malfeasance occurred, the system is too fragile to accommodate the rapid response required for interstellar visitors. In the interim, 30 Atlas continues its journey, oblivious and unconcerned with the political dramas and institutional failures that hinder our study of it. By the time the images are released, if they ever are, the comet will be far from Mars, entering a different phase of its solar transit. The moment will have passed, the opportunity will be lost, and we will be left to ponder what we might have witnessed had we simply been better organized, better prepared, and more committed to the principle that scientific data belongs to everyone and should be shared immediately, not sequestered behind bureaucratic barriers. December will bring new observational opportunities. Hubble and Webb will observe from Earth orbit. Ground-based telescopes will track the object during its closest approach. We will acquire more data, superior data, data that is not ensnared in the labyrinth of a government shutdown. But we will never have another Mars flyby. We will never have another chance at those 30-kilometer resolution images. Whatever they may show, whatever insights they might have provided, that knowledge may remain permanently out of reach. And that, more than any conspiracy theory or allegation of a cover-up, is the true tragedy of the missing Mars images. 9 anomalies and counting. When one studies the universe professionally, an instinct develops for distinguishing the normal from the anomalous. A comet with a slightly unusual orbit? Normal. A comet that outgasses earlier than anticipated? Unusual but not alarming. A comet that exhibits one genuinely perplexing characteristic? Interesting enough for a research paper. But 9 separate properties, each individually stretching the limits of our prior observations. That is when pattern recognition begins to signal unequivocally that something fundamentally different characterizes this object. Let us systematically examine these elements, not as fodder for unfounded theories, but as a straightforward evaluation of what renders Three-Eyed Atlas a source of persistent peculiarity. The first oddity, its orbital inclination. Three-Eyed Atlas follows a path that deviates by a mere 5 degrees from the ecliptic plane, the vast disk within which all the primary planets orbit. For an object originating from interstellar space, entering our solar system from an arbitrary direction in the galaxy, this is an exceedingly improbable alignment. This calculation has been corroborated by numerous independent researchers, estimating the likelihood of an interstellar object naturally possessing this orbital alignment at approximately 1 in 502%. While not strictly impossible, it is certainly not what one would anticipate. The significance of this lies in the fact that the ecliptic plane is the domain of all the planets. If one were to traverse multiple worlds within a single solar system passage, maximizing the opportunities for close encounters with significant celestial bodies, the logical approach would be along the ecliptic, rather than at a steep angle that diverts the trajectory far above or below the planetary disk. Three-Eyed Atlas is projected to pass in proximity to Mars, will approach Venus, and is slated to encounter Jupiter. Its trajectory grants it access to the most pivotal bodies within the inner solar system. Whether by design or by chance, it has selected the optimal route. The second anomaly, the anti-tail, was clearly observed in imagery captured by the Hubble telescope in July and by terrestrial telescopes throughout August. Three-eyed Atlas exhibited an extension of scattered light that pointed towards the sun rather than away from it. Typically, cometary tails are directed away from the sun, repelled by radiation pressure and the solar wind. Anti-tails are not entirely unknown. They can arise from a confluence of viewing geometry and particle dynamics that creates an optical illusion, making a portion of the debris trail appear to face the sun. However, the sustained presence and prominence of this anti-tail in multiple observations of three-eyed Atlas suggest a phenomenon beyond mere geometric perspective. It hints at a physical process actively expelling material in an unconventional direction. Some researchers have posited that this could be interpreted as exhaust from a propulsion system, visible only under specific observational conditions. The prevailing scientific explanation attributes it to a combination of larger dust particles following distinct orbital paths from the comet's nucleus, forming a fan-like debris trail that, from our vantage point, appears to point sunward. Both interpretations are consistent with the observed data. Neither can be definitively proven without closer examination. The third anomaly concerns its velocity. Three-eyed Atlas is traveling at a speed exceeding that of any other measured interstellar object. At the time of its discovery, its velocity relative to the solar system's center of mass was approximately 61 kilometers per second. For comparative context, Oumuamua, the first interstellar visitor, was recorded at 26 kilometers per second, and Comet 2I Borisov at 32 kilometers per second. Three-eyed Atlas is moving at nearly double the speed of the initial interstellar object. This elevated velocity suggests it has been in transit for an immense duration, having been accelerated by gravitational assists from numerous stars over billions of years, accumulating considerable momentum. Alternatively, it implies that it departed its originating system with a substantial initial velocity, propelled by forces beyond gravitational influence alone. A higher velocity also indicates that the object has traversed a greater number of star systems, encountered a wider array of stellar environments, and been exposed to more cosmic radiation throughout its long journey. An object moving at such speed is not making its inaugural passage through a solar system. It is an ancient traveler, and its composition should reflect this extensive history, a matter that is still under investigation. The fourth anomaly is its substantial nucleus. Current estimations place its diameter between 440 meters and 5.6 kilometers. While there is a considerable degree of uncertainty, even the lower estimate renders Three-eyed Atlas significantly larger than Oumuamua. The upper estimate indicates an exceptionally large object, a veritable mountain of ice and rock, adrift in interstellar space. Large comets are generally uncommon, and large interstellar comets should be extraordinarily rare, as ejecting massive objects from planetary systems necessitates extreme dynamical events. Consequently, the probability of detecting such an object during its brief transit through our solar system is exceedingly small. Yet, here it is. Some researchers have pointed out that if the nucleus is indeed at the higher end of the estimated range, measuring 5 or 6 kilometers across, it could not have originated from the typical reservoirs of interstellar ice, as the mass density of large bodies in the interstellar medium is simply too low to permit such detection within a human lifespan. For Three-eyed Atlas to be this massive and to be encountered now would require either an improbable stroke of luck or an origin story vastly different from current assumptions. The fifth anomaly is its early outgassing. The comet became active far beyond the orbit of Jupiter, at a distance of approximately 6.4 astronomical units from the Sun. Most comets originating within our solar system do not initiate outgassing until they are well within Jupiter's orbit, typically closer than 5 astronomical units. This behavior is governed by straightforward thermodynamics. Ice must reach a specific temperature to sublimate at a rate sufficient to produce a visible coma, while carbon dioxide ice, which is believed to be the primary volatile component of three-eyed Atlas, does sublimate more readily than water ice, thus partially explaining the early activity. The intensity of the outgassing and the brightness achieved while still so distant suggests a compositional makeup unusually responsive to weak solar heating. The sixth anomaly, the presence of nickel without a corresponding iron signature, is perhaps its most chemically perplexing characteristic. Spectroscopic observations conducted by the KEK telescope and the Very Large Telescope clearly detected emission lines from nickel atoms within the coma, exhibiting strong and prominent signals. However, no corresponding iron lines were identified. In natural astrophysical contexts, nickel and iron are almost invariably found together. They are synthesized concurrently in stellar cores, condense together in planetary nebulae, and travel together through the interstellar medium. The presence of nickel typically implies the presence of iron. This observation holds true for three-eyed Atlas, with one significant exception. A parallel is found in industrially manufactured nickel alloys produced via the carbonyl process, where nickel tetracarbonyl is formed and subsequently decomposed to yield pure nickel metal. This technique, developed in the 19th century for nickel refining, is not a natural process and does not occur spontaneously in space. Yet, three-eyed Atlas is emitting nickel in a ratio to other elements that mirrors industrial refining, not cosmic chemistry. The standard counterargument suggests that the iron has simply not yet been detected, that its emission lines are too faint or obscured by other spectral features, and that future observations with enhanced sensitivity will reveal iron in the expected proportions, thereby resolving this anomaly. However, multiple independent observations have thus far failed to detect iron. At a certain point, the sustained absence of detection effectively becomes evidence of its absence. The seventh anomaly, the dominance of carbon dioxide, accounts for 87% of the observed volatile emissions, with carbon monoxide at 9% and water at only 4%. For a comet formed in the outer regions of a typical planetary system, this ratio is inverted. Water ice is usually the most abundant volatile, with carbon dioxide as a minor component. The pronounced enrichment of carbon dioxide in three-eyed Atlas suggests formation in an extremely cold environment, possibly in the outer reaches of its origin star system, where temperatures were low enough for carbon dioxide to remain frozen while water ice had already been expelled. Alternatively, it could indicate a very ancient object that has been losing its more volatile components over billions of years, gradually becoming enriched in the less volatile substances that remain. This compositional difference also influences its behavior as it approaches the sun. The sublimation of carbon dioxide generates a cooling effect that suppresses the evaporation of water ice. This may account for the rapid brightening at perihelion that surprised observers. Carbon dioxide outgassing predominated until the comet drew close enough for water ice to begin sublimating in significant quantities, triggering a burst of activity that was not anticipated by models based on typical cometary compositions. The eighth anomaly, the fine-tuned trajectory, is less about a single measurement and more about a series of cumulative geometric coincidences. Three-eyed Atlas arrived aligned with the ecliptic plane. It will pass within tens of millions of kilometers of Mars at a time when multiple spacecraft are actively orbiting the planet. It is scheduled to pass near Venus in early November and near Jupiter in March. Its perihelion occurs when it is geometrically obscured from Earth-based observation by the Sun, making it visible only to solar observatories in space. Each of these circumstances, viewed in isolation, is unremarkable. However, when considered collectively, they describe a trajectory that appears optimized for planetary encounters, while simultaneously minimizing observation by Earth, the solar system's most capable observational platform. Coincidence? Almost certainly. Yet, the alignment of so many geometric factors in a single object prompts researchers to perform probability calculations and publish findings, suggesting that low probability explanations should not be dismissed outright, especially when the consequences of error are substantial. The ninth anomaly, the blue color shift observed at perihelion, was previously discussed, but warrants inclusion in this catalog as it is the most recent addition, the most unexpected, the most difficult to explain through conventional cometary chemistry, and the one that may, if it persists when Three-Eyed Atlas reappears, finally compel the mainstream scientific community to acknowledge that this object is not merely unusual, but genuinely anomalous in ways that necessitate new physics or chemistry for comprehension. 9 anomalies. 9 instances where Three-Eyed Atlas deviates from the expected behavior of interstellar comets. Researchers have assigned the object a score of 4 out of 10 on their scale of potential technological origin. A 4 out of 10 rating does not equate to certainty, nor even a majority probability. However, it is sufficiently high to warrant serious consideration. It is significant enough that dismissing the possibility without thorough investigation would be considered scientifically negligent. The counter-argument, frequently offered by most astronomers when pressed on this subject, posits that space is inherently diverse. Comets exhibit an endless variety of forms, and each object closely observed reveals properties that defy prior expectations. Oumuamua was peculiar. Comet 2I Borisov was surprisingly conventional, yet still possessed unique characteristics. Three-Eyed Atlas, they argue, is simply another data point within the broad spectrum of possible cometary properties. If 100 interstellar comets were observed, 100 different combinations of unusual features would likely be encountered. The fact that Three-Eyed Atlas exhibits 9 anomalies in this view simply places it at the far end of the distribution, not entirely outside of it. This is a reasonable position, a conservative scientific stance often adopted when seeking to avoid extraordinary claims based on limited data. However, it also necessitates accepting a considerable number of coincidences. It requires believing that probabilities as low as 2% can occur naturally, that industrial refining chemistry can manifest spontaneously in space in ways never before observed, that trajectories can optimize themselves for planetary encounters through sheer chance, that objects can coincidentally change color, accelerate and brighten in ways that lack any clear explanation, but must be natural because the alternative is deemed unthinkable. Perhaps all of these improbable events are indeed true. Perhaps Three-Eyed Atlas is simply profoundly unlucky in experiencing so many improbable occurrences simultaneously. Or perhaps the most straightforward explanation, the one requiring the fewest independent coincidences, is that this object is unlike the others, that it is not a comet in the conventional sense, and that it represents something previously unencountered and for which we currently lack the conceptual framework for understanding. Regardless, the list of anomalies is not exhaustive. Should Three-Eyed Atlas continue to defy expectations, and if new observations in November and December reveal further peculiarities, the count will inevitably rise. At some juncture, even the most conservative scientist will be compelled to concede that designating something as anomalous 9, 10, or 11 times is merely another way of stating that we have no understanding of what we are observing. The gamble of the JUICE mission. There exists a spacecraft currently in operation that has already captured the very discovery we are all anticipating. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, conducted its observations of Three-Eyed Atlas between November 2nd and November 25th, 2025, utilizing multiple instruments, including cameras, spectrometers, and particle sensors. The spacecraft was ideally positioned to observe the comet in the immediate aftermath of its perihelion passage, during the crucial period when any significant outgassing resulting from the unexplained acceleration should still be observable, continuing to generate a bright, expanding cloud of debris that would be unmistakably evident in the collected data. JUICE did observe it. Whatever phenomena are currently affecting Three-Eyed Atlas, whatever its state as it recedes from the sun, JUICE has already recorded that information. The photons have struck the detectors. The data has been captured. The observations are complete. However, we will not ascertain their contents until February 2026, 3 months. 3 months of waiting while the most critical data pertaining to Three-Eyed Atlas resides within the computer memory of a spacecraft too distant from Earth to transmit it promptly. 3 months of speculation, debate, analysis of older observations, and mounting frustration among astronomers who are aware that the answers they seek have already been collected, but remain entirely inaccessible. This is the inherent reality of deep space missions. This is the price we pay for dispatching instruments to the outer solar system, where communication is protracted and bandwidth is a precious commodity. Let me elucidate precisely why JUICE's observations are of such paramount importance, potentially exceeding the value of any data gathered by the Hubble or Webb telescopes or terrestrial observatories in December. It all hinges on timing and observational perspective. When Three-Eyed Atlas reached perihelion, it did not enter a position behind the sun from JUICE's viewpoint. The spacecraft is operating on a completely different trajectory, currently executing gravitational assists as it navigates towards the Jovian system. From JUICE's location, Three-Eyed Atlas remained visible throughout its perihelion passage. More significantly, JUICE was observing the comet during the days and weeks immediately following perihelion, when solar heating remained intense, when any outgassing should have been at or near its peak, and when the acceleration detected by Phoenicia would have been producing observable effects. If the predictions are accurate, and if the non-gravitational acceleration requires a 10% mass loss to be explained by natural rocket effects, then JUICE should have witnessed a substantial coma, an immense cloud of gas and dust, far larger and brighter than anything observed prior to perihelion. The particle sensors would have registered elevated densities of ions and neutral particles. The spectrometers would have quantified the composition and temperature of the expelled material. The cameras would have captured images of the coma's structure, revealing whether the emissions were symmetrical or emanated from specific active jets on the nucleus. All of this data currently exists, stored within JUICE's memory banks, awaiting transmission. The reason for this delay is not mysterious or suspicious. It is purely technical. JUICE is currently situated approximately 2 astronomical units from Earth and is continuing to move further away. At this distance, radio signals require about 16 minutes to traverse one way. The spacecraft utilizes its main high-gain antenna as a heat shield. During certain phases of its trajectory, this necessitates reliance on the smaller medium-gain antenna for communication. The medium-gain antenna possesses a significantly lower data transmission rate, causing everything to proceed at a slower pace. Scientific data is prioritized and queued, with observations transmitted in the order they were acquired, ensuring that the most time-critical information is sent first. The observations of Three-Eyed Atlas, while scientifically compelling, are not the primary mission objective. JUICE was designed to investigate Jupiter's icy moons, Europa, Ganymede, and Callisto. These celestial bodies represent the primary scientific return for the mission, and it is to their study that the mission operations team is dedicated. The cometary observations were an incidental opportunity, a target of convenience, something the spacecraft could observe because it happened to be in the right place at the right time. However, they do not dictate the data transmission schedule. Consequently, we wait. We wait as JUICE continues its voyage. We wait as the data slowly trickles back to Earth at kilobits per second. We wait as Three-Eyed Atlas diminishes in brightness and recedes into the distance, while the opportunity to correlate JUICE's findings with contemporaneous Earth-based observations slips away. This situation is deeply frustrating for researchers eager for immediate answers, who need current information to plan December observation campaigns without knowledge of JUICE's existing discoveries. Should they focus on measuring coma density, attempting to detect that predicted massive gas cloud? Or has JUICE already determined that no such cloud exists, rendering those measurements a waste of valuable telescope time? Should they prioritize spectroscopy, searching for emission lines that might explain the blue coloration? Or has JUICE already identified the source, making further spectral analysis redundant? In the absence of JUICE's data, astronomers are operating blindly, planning observations based on incomplete information, on predictions that may already be invalidated, and on questions that might already possess answers. This is not an efficient methodology for conducting scientific research, but it is the current reality of the situation. JUICE will not suddenly download terabytes of data simply due to the impatience of the astronomical community. The spacecraft adheres to its established timeline, and the data will arrive when it arrives. We must adapt. Furthermore, there is the question of JUICE's actual observational capabilities at its recorded distance. The closest approach between JUICE and Three-Eyed Atlas occurred on November 4th, when the separation was approximately 64 million kilometers. To provide perspective, this is roughly 40% of the distance between the Earth and the Sun. From this range, even JUICE's sophisticated instruments cannot resolve fine details on the nucleus. The Janus Visible Light Imager possesses excellent resolution, but not to the extent required to distinguish surface features from tens of millions of kilometers away. What JUICE can accomplish is to measure the overall brightness, the dimensions and shape of the coma, and the distribution of material surrounding the nucleus. The MAGIS infrared spectrometer is capable of identifying molecules based on their absorption and emission lines, thereby determining the types of ice and gas present. The SWI sub-millimeter wave instrument can detect specific molecular species that are difficult to observe at other wavelengths. The particle sensors can directly sample any gas or dust that may be encountered in the spacecraft's vicinity, although at 64 million kilometers, the density of cometary material is likely too low to yield significant readings. Nevertheless, the combined operation of all these instruments, simultaneously observing the same target from the same vantage point, will yield a data set that no single terrestrial telescope can match. Simultaneous multi-wavelength observations are incredibly powerful for constraining physical models. When a specific feature is observed across visible light, infrared, and sub-millimeter wavelengths, concurrently, the temperature, composition, and dynamics of the emitting material can be determined with far greater certainty than when attempting to piece together observations made at different times from disparate locations. NASA's Europa Clipper mission was also intended to coordinate observations with JUICE. Both spacecraft are equipped with ultraviolet spectrographs designed to study the tenuous atmospheres and exospheres of icy moons. These instruments can also be directed towards comets. The intention was that simultaneous ultraviolet observations from two distinct spacecraft would provide stereoscopic views of the coma, revealing three-dimensional structures that cannot be captured by single-point observations. The actual execution of that coordination, and whether Europa Clipper managed to pinpoint 3 Atlas during the designated observation period, remains unconfirmed. No official pronouncements have been issued, and no preliminary findings have been disclosed. We are left in a state of uncertainty and anticipation. The date of February 2026 seems incredibly distant from our current vantage point. By the time that month arrives, 3 Atlas will have completed its closest pass to Earth. The observations planned for December will have concluded. Both the Hubble and James Webb Space Telescopes will have gathered their respective data. Ground-based observational campaigns will also be finished. The scientific community will have formulated initial hypotheses based on all available information, with the exception of the data from JUICE. Then, 3 months later, the JUICE data will become accessible, potentially validating all our existing assumptions. Alternatively, it could completely alter our understanding, revealing that the processes we believed were occurring at perihelion were nothing like the reality. This inherent uncertainty represents the gamble and the frustration associated with studying transient celestial events using communication systems that operate at a slower pace. We are compelled to make critical decisions, schedule observations, and submit research papers without access to data that already exists, but cannot be retrieved quickly enough to inform these very choices. It's akin to attempting to complete a jigsaw puzzle while someone deliberately withholds certain pieces, promising their eventual delivery, but not at the crucial moment when they are needed. Some have proposed that the European Space Agency should alter its data transmission priorities, suggesting that 3 Atlas is significant enough to warrant bringing its observations to the forefront of the queue. However, this is not how mission operations function. The entire data management plan cannot simply be rewritten because a particular target of interest proves to be more compelling than initially anticipated. There are contractual commitments to the instrument teams, pre-established schedules for various scientific objectives, and bandwidth limitations that were determined years in advance during the mission's planning phase. Modifying all of these elements on the fly would lead to widespread disruption, endanger other scientific endeavors, and necessitate approval from numerous hierarchical levels. Such a scenario is highly improbable. The data will arrive according to the predetermined schedule. We will gain access to it in February. Until then, we are left to our own devices. The situation is further complicated by the possibility that JUICE's observations might constitute the sole reliable record of 3 Atlas in its immediate post-perihelion state. By the time the comet reappears in Earth's view in mid-November and telescopes can reacquire it, several weeks will have elapsed since its closest approach to the Sun. If the object underwent significant and rapid changes during this period, for instance, a dramatic surge in brightness followed by a rapid dimming, or the expulsion of a burst of gas that subsequently dispersed, we will have missed observing these critical events. The only record of this pivotal transition will reside within the JUICE data, and if this data contradicts what ground-based telescopes observe in late November and December, if the comet appears different from the state captured by JUICE just weeks prior, we will be faced with the challenge of explaining not one, but 2 sets of discrepancies. The Earth approach on December 19th will still hold considerable value, yielding high-resolution imagery, detailed spectral analysis, and precise photometric measurements. However, it will be observing a comet that has been significantly removed from perihelion for nearly 2 months. This comet will have cooled down, reduced its gas emission rate, and potentially altered its appearance and behavior. We will be observing 3 Atlas in a distinct condition compared to its state when viewed by JUICE. Comparing these 2 datasets will necessitate meticulous modeling and assumptions regarding cometary evolution as they recede from the Sun, leading to extrapolations that introduce a degree of uncertainty. If only we had access to the JUICE data now. If only we knew what 3I Atlas looked like in early November, we could have planned the December observations far more effectively. We could have targeted specific features, validated or refuted particular hypotheses, and utilized our limited telescope time on questions of genuine importance rather than engaging in a blind search for answers. But we are unable to do so. Therefore, we wait. We theorize. We prepare for December without any knowledge of what JUICE has already revealed. And we hold out hope that when February finally arrives and the data finally reaches Earth, it will have justified the prolonged wait. We hope it will provide answers to the questions that have occupied us for months and ultimately clarify whether 3 Atlas is an exceptionally unusual comet or something entirely different. 3 months. In the grand scale of a multi-year space mission, this duration is not substantial. However, at this moment, with 3I Atlas dominating headlines, fueling debates, and keeping astronomers awake at night, pondering its nature, 3 months feels like an interminable period. It is a struggle against the prevailing consensus. The dispute is not truly about 3I Atlas itself, but rather about how the scientific community should respond to anomalies, the weight to be assigned to improbable explanations, and whether the potential for a truly revolutionary discovery justifies the reputational risk of being demonstrably incorrect. Avi Loeb has unequivocally stated his position. When an object exhibits 9 unexplained characteristics, and the combined probability of all these anomalies occurring naturally falls below a certain threshold, there is a scientific imperative to consider alternative explanations, even those that are uncomfortable or sound like science fiction. The established astronomical community vociferously disagrees. Brian Cox, a renowned physicist and science communicator, articulated his viewpoint plainly. 3I Atlas is a comet composed of carbon dioxide and water ices, along with other materials. It follows a predictable orbit. It will traverse the Sun and continue its journey through the galaxy. He describes the speculation regarding alien origins as drivel, sensationalism, and a misrepresentation of scientific processes and evidence. Loeb's rejoinder was equally direct. He likened Cox to a primitive individual who, upon finding a telephone, dismisses it as merely a rock. Loeb contends that true scientists engage with the data in the field, whereas commentators merely reiterate popular opinions from the sidelines. The implication is evident. Cox, in Loeb's view, is not conducting science but performing for an audience, adopting a safe stance that avoids controversy or ridicule, thus preserving his reputation as a reliable scientific authority. However, Loeb argues that such cautious approaches do not foster discovery. They merely reinforce existing beliefs. This division, this fundamental divergence in perspectives on scientific methodology and risk tolerance, has become the underlying theme of every discussion surrounding 3 Atlas. The core issue transcends whether the comet is natural or artificial. It questions whether such an inquiry should even be voiced aloud. Tom Statler from NASA represents the institutional viewpoint. He maintains that the object appears to be a comet, behaves like a comet, and bears a strong resemblance to known comets. While acknowledging its unusual properties and slight deviations from the behavior of solar system comets, he asserts that the overwhelming evidence points to a natural origin. To suggest otherwise based on the limited data currently available, he believes, is premature and irresponsible, creating unwarranted public uncertainty and damaging the credibility of the scientific endeavor. Loeb has encountered similar criticisms previously. He faced them when he proposed that Oumuamua might be artificial, when he published his hypothesis concerning light sails and interstellar probes, and when he established the Galileo project to search for technological signatures within astronomical data. The critique has been remarkably consistent. You are being excessively speculative. You are not adhering to rigorous scientific standards. You are chasing headlines instead of conducting proper science. And you are eroding public trust by entertaining notions lacking a solid evidential foundation. However, the underlying issue with this criticism is that Loeb is not disregarding evidence, nor is he fabricating information. He is examining the same data as everyone else, but reaching a different conclusion about what warrants attention. He assigns greater significance to the anomalies and less weight to conventional explanations, calculating that the probability space for exotic hypotheses is broader than most of his peers acknowledge. This, he argues, is not unscientific. It represents a distinct approach to reasoning under conditions of uncertain evidence. Consider the detection of nickel without a corresponding iron signature. The conventional explanation posits that iron is present but has not yet been detected, and that future observations will locate it. This is a plausible and conservative hypothesis, requiring neither new physics nor new chemistry. However, it is also unfalsifiable in the short term. One can perpetually claim that insufficient observation has occurred whenever new data fails to reveal iron. At what juncture, then, should one accept that the absence of iron might be genuine, and that the chemical composition of 3 Atlas is indeed distinct from anything previously observed? Loeb's stance is that observations should be taken at face value. If multiple independent spectrographs across various instruments have failed to detect iron, the possibility of its absence should be seriously considered. If there is indeed no iron, and nickel is being emitted without its customary accompanying element, then an explanation for this phenomenon is required. The carbonyl refining process, an industrial procedure associated with technological manufacturing, offers one such explanation. While this does not definitively prove that 3 Sao Atlas is artificial, it suggests that the possibility should not be dismissed without further investigation. The scientific establishment exhibits a reflexive, almost immunological response to suggestions of alien technology. This is understandable, given the field's past experiences with unfounded speculation that ultimately proved incorrect. Pulsars were briefly considered artificial beacons before the understanding of neutron stars emerged. Fast radio bursts ignited speculation about advanced civilizations before natural mechanisms for their production were identified. The historical pattern of the WOW signal, the face on Mars, and the canals of Venus, where extraordinary explanations were eventually refuted by natural phenomena, has cultivated a bias. When an individual like Loeb suggests an interstellar object might be artificial, the immediate reaction is not to evaluate the claim on its merits, but rather to associate it with previous erroneous alarms. It evokes parallels to the Face on Mars episode, or the perception of someone desperate for attention making unsupported assertions, thereby appearing to engage in poor scientific practice. However, this pattern matching can also be fallible. The fact that previous claims of alien technology were incorrect does not preclude the possibility that all such claims are incorrect. The universe is not bound by our expectations. It is entirely conceivable that within the vast spectrum of astronomical phenomena, genuine evidence of technology created by non-human intelligence exists. If such evidence were to appear, it would initially manifest as anomalies, violating our expectations and appearing too improbable to be true. The scientists who bring such findings to light would likely face criticism and ridicule, accused of sensationalism and poor judgment, until sufficient data accumulates to render the conclusion undeniable. Loeb contends that we are currently in this initial phase with 3I Atlas, arguing that the anomalies are significant enough to warrant serious investigation. He posits that assigning a 30 to 40% probability to a non-natural origin is not wild speculation but a reasonable assessment given the available evidence. He warns that dismissing this possibility prematurely, or closing off this line of inquiry due to discomfort, could be a repetition of historical scientific errors, such as the dismissal of continental drift, the rejection of meteorites, or the insistence on a static and eternal universe. His critics maintain that extraordinary claims necessitate extraordinary evidence, and they argue that the evidence for 3I Atlas being anything other than a comet is, at best, suggestive, not extraordinary. They believe the anomalies can all be explained through conventional physics. The fact that these explanations require the simultaneous occurrence of several unlikely events does not, in their view, justify abandoning natural explanations in favor of unproven alternatives. Darrell Seligman from Michigan State University aligns with this perspective. Having extensively studied 3 Atlas and published papers on its composition and trajectory, he is confident in its cometary nature. He asserts that the non-gravitational acceleration is consistent with comets, that the nickel emission, while unusual, does not necessitate exotic chemistry for an explanation, and that the orbital alignment, though improbable, is not impossible. He also notes that the high velocity, while notable, falls within the expected range for objects ejected from nearby star systems billions of years ago. Seligman contends that each individual anomaly possesses a plausible natural explanation. Loeb's response is that this approach misses the fundamental point. The issue is not whether each anomaly can be explained in isolation, but rather whether the collection of anomalies, when considered together, is more readily explained by one hypothesis over another. In his judgment, an artificial object would naturally exhibit precisely the suite of properties observed in 3I Atlas. Such an object would be aligned with the ecliptic to facilitate access to multiple planets. Its unusual chemistry would stem from manufactured materials rather than natural ices. Non-gravitational acceleration would be present if it possessed propulsion systems. Its large size and high velocity would be consistent with its design for interstellar travel. Its color changes could indicate internal systems generating heat or emissions. Loeb repeatedly acknowledges that none of this constitutes definitive proof. However, he argues that proof is not the standard that should be applied at this initial stage. The relevant standard, he posits, is whether the hypothesis warrants investigation, resources, attention, and follow-up observations. His unequivocal answer is yes. The rationale is that the potential consequences of being correct are so immense that even a 10% or 5% probability justifies the effort required to ascertain the truth. The counterargument posits that pursuing low-probability hypotheses is a waste of limited resources. Telescope time is precious, and funding is scarce. Diverting attention to unlikely explanations, critics argue, means missing opportunities to study phenomena known to be real and important. Furthermore, it risks conditioning the public to expect extraterrestrial encounters at every turn, creating a boy who cried wolf scenario, where genuine discoveries are met with skepticism due to the field's saturation with false positives. This is the impasse. Both sides present valid arguments and operate from defensible positions within the framework of scientific methodology. Both sides experience profound frustration with each other, as the disagreement is not truly about the data itself, but about underlying values, the types of risks deemed acceptable, and whether it is more detrimental to miss a genuine discovery through excessive conservatism or to squander resources on speculation due to excessive credulity. 3. Atlas has inadvertently become the battleground for this larger conflict. Every new observation, every anomaly, every unexplained brightening or shift in color is interpreted through these opposing analytical lenses. Loeb perceives accumulating evidence supporting his hypothesis. His critics, conversely, see confirmation of their skepticism, interpreting the object's behavior as revealing itself to be unusually natural after all. The observations in December will not resolve this debate. Regardless of what the data reveals, both sides will find interpretations that align with their pre-existing beliefs. If the comet exhibits the predicted massive gas cloud, Loeb's critics will proclaim it as natural outgassing, precisely as they anticipated. If the comet fails to display such a cloud, Loeb will argue that the rocket effect cannot account for the acceleration, indicating something else is at play. The evidence will remain inconclusive, as it often is. There will invariably be room for alternative interpretations, additional hypotheses, and continued observation. The only means to definitively settle the question would be through close-up observation, a dedicated spacecraft mission to 3I Atlas. Such a mission would require cameras capable of resolving surface features, instruments to directly sample the coma, and potentially even a lander to determine its composition and structure with absolute certainty. However, such a mission does not currently exist and cannot be launched in time. 3 Atlas will have departed the solar system before we could reach it. Consequently, the debate persists, Loeb versus the world, with everyone watching, waiting to see who history will deem correct. The brightening that defied established models. Chichang Jiang from Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory have dedicated years to tracking comets. They possess a profound understanding of how comets brighten as they approach the sun, including the governing equations, the underlying physics, and the empirical relationships that link heliocentric distance to apparent magnitude. As a comet draws nearer to the sun, its temperature rises, accelerating the sublimation of ice and releasing more gas and dust, which in turn causes the coma to expand and brighten. This process is predictable and follows established power law relationships. By knowing a few fundamental parameters about a comet's composition and size, its expected brightness at any given distance can be calculated. 3 Atlas, however, deviated from these established norms. Between September and October 2025, as it descended toward perihelion, its brightness increased at a rate that significantly surpassed all predictions. This was not a minor variation, nor was it within the expected range for comets that exhibit slightly higher activity or dust content than average. Instead, the deviation was so substantial that it necessitated the addition of supplementary terms to the governing equations, strongly suggesting that something fundamentally different was occurring within or around the object. The numerical data tells a compelling story. During the initial phase of its approach, 3 Atlas brightened at a rate roughly consistent with expectations, adhering to a power law where brightness increased proportionally to the distance from the sun, raised to a negative exponent. Typical comets exhibit exponents around -3 or -4, meaning that as they approach twice as close to the sun, they become approximately 8 to 16 times brighter. 3 Atlas followed a similar pattern through July and August, allowing observers to predict its magnitude a few weeks in advance with reasonable accuracy. However, in September, a significant change occurred. The rate of brightening accelerated, and the observed data began to diverge from the model predictions. By early October, when space-based solar observatories were able to track the comet as it moved behind the sun, from Earth's perspective, the brightening had become extreme. Jiang and Battams calculated that 3-2 Atlas was following a power law with an exponent of approximately 7.5 plus or minus 1. This represents a rate of brightening nearly double that of normal comets, meaning that each day closer to the sun resulted in a dramatic increase in its apparent magnitude. The significance of this observation extends beyond mere aesthetics. Brightness serves as a proxy for activity. An increase in a comet's brightness indicates that a larger surface area is actively undergoing sublimation, releasing more ice as gas and ejecting more dust from the nucleus. Consequently, the total energy budget of the system increases, and this energy must originate from a source. For a typical comet, this source is solar heating. Sunlight strikes the surface, warming the ice and driving sublimation. The rate of this process is dependent on the amount of sunlight absorbed, which in turn is determined by the distance from the sun. Being twice as close to the sun results in 4 times the solar energy per unit area, leading to faster sublimation, but not at the rate indicated by a power law of 7.5. Something else must be contributing to this accelerated brightening. One plausible explanation is that the comet underwent a compositional transition. Earlier in its approach, when it was farther from the sun, carbon dioxide ice was the dominant volatile substance. Carbon dioxide readily sublimes even at low temperatures, which accounts for 3I Atlas beginning to outgas beyond Jupiter's orbit. However, carbon dioxide also has a cooling effect. As it evaporates, it absorbs heat from the surrounding material, lowering the surface temperature and suppressing the sublimation of other ices, particularly water. The prevailing theory suggests that as the celestial body known as 3 Atlas drew nearer to the Sun, its surface layers, composed of carbon dioxide, either depleted or retreated inward, unveiling a previously shielded layer of water ice. This water ice, upon reaching a specific thermal threshold, undergoes sublimation at a considerably accelerated rate. The thermal energy required for this phase change, known as the latent heat of sublimation, differs significantly from other transitions, and the vapor pressure characteristics are also distinct. Consequently, a sudden surge in activity can occur when water ice becomes the predominant volatile substance. This transition would not manifest as a gradual alteration in observational data, but rather as an abrupt escalation in the comet's luminosity around its closest approach to the Sun, termed perihelion. This explanation appears plausible, aligning with the known chemical properties of 3 Atlas and avoiding the need for novel physical principles. However, it necessitates a very precise set of circumstances. The carbon dioxide layer must possess sufficient thickness to inhibit water sublimation for an extended period, yet be sufficiently thin to erode away at precisely the opportune moment to produce the observed brightening surge. Furthermore, the comet's nucleus must exhibit a layered structure with carbon dioxide situated atop water ice, a configuration that contradicts expectations for a comet forming in a frigid environment where carbon dioxide would typically freeze first and be found deeper within the core. An alternative hypothesis, which Zhang and Batams deliberately refrained from explicitly articulating, but which lingers in discussions of this data, posits that the observed brightening is not solely attributable to sublimation. This alternative suggests that an additional energy source is contributing to the luminosity, implying that something within 3 Atlas is generating heat or releasing stored energy in a manner that supplements solar heating, thereby producing a brightening profile that natural processes alone cannot replicate. Lowe has enthusiastically embraced this concept, noting that the blue coloration observed during perihelion is consistent with emissions originating from a source hotter than what would be expected from passive solar absorption. If 3 Atlas possesses an internal power source, generating energy through mechanisms other than direct sunlight absorption, that energy must be dissipated. This energy would consequently heat the surface, drive additional sublimation, and render the comet brighter than predictions based solely on solar heating. Moreover, it would produce spectral signatures, specifically emission lines and colors, that deviate from those associated with reflected sunlight passing through a cloud of dust and gas. The prevailing scientific consensus dismisses this notion as unnecessary speculation, arguing that invoking an internal power source to account for the brightening requires the assumption of an entity for which there is no independent corroborating evidence. While the compositional transition theory demands specific conditions, it is considered significantly more probable than the hypothesis that 3 Atlas harbors an energy source of unknown origin. Occam's razor suggests favoring the simpler explanation. However, the definition of simplicity is debatable. Is it simpler to postulate a highly specific layered structure with exact compositional boundaries that coincidentally produce a brightening surge at a time when the comet is unobservable from Earth? Or is it simpler to assume that an object exhibiting 9 other anomalies possesses a 10th anomaly that is mechanistically linked to the preceding 9? The answer is contingent upon one's pre-existing beliefs about 3 Atlas. If one is convinced it is a naturally occurring comet, then any naturalistic explanation, however elaborate, would be deemed simpler than an artificial one. Conversely, if one remains open to the possibility that it represents something else entirely, then adding another piece of evidence supporting that hypothesis becomes the more straightforward approach. What renders the brightening particularly enigmatic is the absence of a complete light curve. We possess observations from preceding perihelion, documenting the acceleration of its luminosity. We also have space-based observations from the precise moment of perihelion, indicating that the comet achieved extraordinary brightness, exhibiting a bluer hue than the Sun, and emitting strongly in wavelengths suggestive of gas rather than dust. Crucially, we lack continuous observations that would reveal whether the brightening peaked and subsequently declined, plateaued, or even continued to increase beyond perihelion, at which point a fading would be anticipated. This void in the observational record is profoundly frustrating. Had we access to the post-perihelion light curve, and were we aware of the rate at which 3 Atlas diminished in brightness, or indeed whether it faded at all, our modeling capabilities would be significantly enhanced. A rapid decline would imply that the brightening was a transient event, perhaps caused by a substantial fragment of the nucleus detaching and creating a sudden release of exposed ice that then quickly dissipated. A plateau would suggest sustained high activity, a scenario more difficult to explain through passive solar heating unless the nucleus is considerably larger than initially estimated. A continuous increase would be exceedingly challenging to explain through naturalistic means and would strongly support the notion that factors other than solar proximity are dictating the comet's luminosity. It is possible that the JUICE mission possesses this crucial data, as the spacecraft was actively observing during the critical period. JUICE could have recorded the comet's brightness daily, charting the evolution of its light curve through perihelion and into the post-perihelion phase. However, this data will not be accessible until February. Consequently, we are left to conjecture, constructing models based on incomplete information, with the hope that the eventual revelation of the complete picture will illuminate the current observations. Amateur astronomers have endeavored to bridge this observational gap. A skilled comet hunter, Ahati Boone, identified 3 Atlas in 69 images captured between October 18th and October 24th. His observations indicated that the comet remained bright, comparable in luminosity to nearby stars at magnitude 11, even as it receded from perihelion. This suggests sustained activity rather than a fleeting outburst. However, these observations are constrained by the capabilities of a weather satellite's solar monitoring camera, which was not designed for precise photometry of faint comets, resulting in significant error margins and calibration uncertainties. While superior to having no data, it is not conclusive. Ground-based observations are scheduled to resume in mid-November, coinciding with 3 Atlas's emergence from behind the Sun. Numerous telescopes will be employed to measure its brightness, track its changes over the subsequent weeks, and compare this data with pre-perihelion observations. If the comet exhibits significantly greater brightness than in September and maintains a high level of activity as it moves farther from the Sun and cools, this would constitute a major clue regarding the events at perihelion. Conversely, if it has faded to expected levels and now follows a typical power law decline, it would suggest the brightening was a temporary phenomenon, a phase transition, or a compositional peculiarity that has since passed. Nevertheless, a third possibility exists, one that most are hesitant to openly contemplate. What if 3 Atlas's brightening does not conform to any power law, neither conventional nor anomalous? What if its luminosity fluctuates in ways entirely uncorrelated with its distance from the Sun? What if we observe sporadic flares, sudden increases followed by declines, patterns indicative of internal processes rather than external heating? Such a scenario would provide the strongest evidence to date that something profoundly unusual is occurring with this object, compelling even skeptics to acknowledge that 3 Atlas is behaving unlike any comet ever studied. The brightening phenomenon that defied established models is not merely an academic curiosity. It serves as a portal into the internal mechanisms of 3 Atlas. Every photon reaching our telescopes carries information about its origin, its creators, and the processes active on or within the comet. When these photons arrive in quantities exceeding our expectations, when they form a light curve that defies our equations, they signal that our current understanding is incomplete. This implies either that the comet's composition is more peculiar than we previously imagined, its structure more intricate than assumed, or that an additional energy source beyond solar provision is at play. The month of December promises to yield more photons, additional data points, and a more refined light curve, ultimately leading to an understanding of why 3 Atlas brightened in the manner observed. We will develop a model that accurately reflects the observations and publish scientific papers detailing the associated physics and chemistry. However, whether that explanation will involve natural processes or more exotic phenomena remains to be determined. For the present, we are left with a comet that defied predictions, shattered models, and leaves us pondering its future actions before its permanent departure from our solar system. The transformations in color, red in July, green in September, and blue in October, represent 3 distinct states of matter and energy within the coma of 3 Atlas over a period of 4 months. This behavior deviates significantly from typical cometary activity. While comets can indeed alter their color as they approach the sun due to the sublimation of different ices at varying temperatures and shifts in the balance between dust and gas, the specific progression observed, from red to green to blue, narrates a chemical sequence that proves difficult to reconcile with established knowledge. Initially, in July, when 3 Atlas was first scrutinized in detail and captured by the Hubble Space Telescope, revealing its unusual anti-tail, its color signature was predominantly reddish. This coloration is attributed to dust, specifically carbonaceous grains and organic materials that had been subjected to billions of years of cosmic radiation during interstellar travel, reflecting sunlight. This is characteristic of a comet still relatively cold and distant from the sun, where sublimation is just commencing and its coma is primarily composed of solid particles rather than gas. Red signifies dust, passive reflection of sunlight, and a seemingly normal state of affairs. Subsequently, on September 7th, during a total lunar eclipse, astrophotographers Michael Jagger and Gerald Riemann documented 3 Atlas from Namibia, displaying a distinct blue-green hue. The comet's coma, measuring 2.5 arc minutes across, was clearly discernible in both blue and green filters. This color is classically associated with comets, indicating fluorescence from diatomic carbon, C2 molecules, energized by the sun's ultraviolet radiation. It signifies the breakdown of organic compounds and complex carbon chains under solar influence, emitting a characteristic emerald glow as electrons return to their ground state. However, a complication arises. Prior spectroscopic analyses conducted by the Very Large Telescope and KEK revealed that 3 Atlas exhibits unusually low concentrations of carbon chain molecules. A paper authored by Luis Salazar Manzano specifically noted that 3E Atlas ranks among the comets with the most depleted carbon chains known, exhibiting an extremely high ratio of cyanogen to C2, implying a scarcity of the molecule typically responsible for green emission. This raises the question, from whence did the green color originate? One possibility is that the spectroscopic observations were incomplete, and C2 was present but at levels too low to be detected with the available integration times and sensitivities. As the comet drew nearer to the sun and sublimation intensified, sufficient C2 might have accumulated in the coma to produce visible green fluorescence. In this scenario, the molecule was always present, but remained below the detection threshold until conditions became favorable. Another potential explanation is that the green emission was not derived from C2. Certain other molecules can produce green emissions under specific circumstances. For instance, some nickel compounds, when excited by ultraviolet light, can fluoresce at wavelengths perceived as greenish. Given that 3I Atlas is emitting nickel in unusual quantities, and notably without its typical iron companion, it is conceivable that the green phase was related to metal chemistry rather than carbon chemistry. This would imply that we were observing the signature of nickel tetracarbonyl decomposing, releasing nickel atoms that subsequently absorbed and re-emitted light in the green spectrum. This is speculative, as nickel fluorescence has not been previously measured from a comet, nor has any comet exhibited prominent nickel emission before. We are navigating uncharted territory and attempting to explain observations that do not align with existing frameworks. However, if the green phase was indeed linked to nickel rather than carbon, it would integrate into the broader pattern of chemical anomalies, providing further evidence that 3 Atlas possesses a unique composition. Subsequently, the comet turned blue, not merely tinged with blue, but intensely and remarkably blue, surpassing the Sun in blueness. This is where conventional explanations begin to falter significantly. Blue emission from a comet, while rare, is not entirely unprecedented. Ionized carbon monoxide can fluoresce in blue wavelengths when subjected to solar wind particles and ultraviolet radiation. The ion tail of a comet, which points directly away from the Sun and is influenced by magnetic fields rather than radiation pressure, often appears blue due to its composition of ionized molecules rather than neutral gas or dust. Therefore, observing some blue coloration in the spectrum of 3 Atlas would not be surprising. However, this was not merely a hint of blue, it was a dominant blue. Color observations from Stereo and GOAS 19 consistently indicated that the comet's coma emitted more strongly in blue wavelengths than in red. For an object theoretically cooler than the Sun, expected to have dust scattering its reflected light, and predicted to produce emissions primarily from molecules with characteristic wavelengths in the ultraviolet, visible green, or near-infrared, a blue dominance is anomalous. It suggests a thermal spectrum hotter than anticipated, or emission from a source that preferentially generates blue light through a mechanism other than simple fluorescence. The thermal interpretation encounters immediate obstacles. For 3 Atlas to exhibit a thermal spectrum peaking in the blue, its surface or coma temperature would need to reach several thousand Kelvin. This temperature range is hotter than most stars and exceeds that of any natural object in the solar system apart from the Sun itself. It is astrophysically improbable for ice to be heated to such temperatures by sunlight at a distance of 1.36 astronomical units, nor can rock be heated to comparable temperatures at that range. If the blue color is thermal, representing blackbody radiation from a hot surface, then the heat source must be internal, not solely solar-driven. This leads back to the question of internal energy sources. What could generate sufficient internal heat within a comet to produce visible blue emission? Natural radioactive decay is far too weak, even if 3 Atlas contained an exceptionally high concentration of uranium or thorium. The heat generated would be negligible compared to the required amount. Chemical reactions, such as those occurring if the nucleus contained pockets of volatile compounds that suddenly mixed and reacted, could generate heat. However, sustaining this heat for the duration necessary to account for the observed emission, and doing so in a manner that produces blue dominance rather than a broad thermal spectrum, necessitates highly specific and seemingly contrived conditions. The alternative, which Lowe has alluded to without explicit declaration, is that the blue emission is not thermal in nature. Instead, it could be line emission from an unidentified molecule or process, suggesting that 3 Atlas is releasing energy through a mechanism that naturally produces blue photons, and we are witnessing the signature of this mechanism in the color data. The specific nature of such a mechanism, or the type of chemistry or physics, capable of producing such emission without corresponding spectral features in other parts of the spectrum, remains unclear. We lack a plausible natural candidate, or the emission is not natural. If 3 Atlas possesses internal systems, including power generation and waste heat dissipation, the color of that radiation would depend on the temperature of the radiating surface and the materials involved. Certain industrial processes, types of lighting, and plasma states all produce characteristically blue emissions. A spacecraft operating on a nuclear reactor would exhibit a thermal spectrum dictated by the reactor's operational temperature. A probe utilizing ion engines would generate a blue glow from the ionized propellant. These are engineering phenomena, not astronomical ones. However, if one considers the possibility of an engineered object rather than a natural one, such phenomena would be expected. This is where the progression of colors becomes particularly compelling. The shift from red to green to blue does not align with a natural sequence based solely on temperature. If 3 Atlas were simply heating up as it approached the sun, one would anticipate a color shift from red toward yellow, potentially evolving to white as the thermal spectrum shifted towards shorter wavelengths. A discrete progression through color phases, each dominated by different emission mechanisms at different times, would not be expected. This suggests evolving chemistry, changing composition, and the activation of different processes as conditions transform. A layered nucleus could potentially explain this. Initially, dust dominates as only the surface is active. Later, as this dust layer erodes, underlying carbon-rich ices begin to sublimate, producing green emission. Even later, at its closest approach, water ice deep within the interior finally reaches sublimation temperature, and the coma becomes dominated by water vapor and its dissociation products, some of which might emit in blue wavelengths under intense solar ultraviolet radiation. This narrative is plausible and requires a very specific nuclear structure, though it is not physically impossible. What is required to resolve this enigma is spectroscopy, high-resolution spectra capable of identifying individual molecular emission lines, measuring ratios, temperatures, and velocities. The color observations indicate that something unusual is occurring, but do not reveal its precise nature. To ascertain this, we must decompose the light into its constituent wavelengths, identify the present molecules and their abundances, and map the coma's chemistry in detail. The observations scheduled for December will encompass extensive spectroscopic campaigns, with the Hubble, Webb, Gemini telescopes, KEK, and the Very Large Telescope, all equipped with spectrographs, trained on 3 Atlas during its closest approach. The data they collect will either confirm that the blue color originates from known molecular emissions, prompting an update to our models and further research, or it will reveal something unexpected, spectral signatures that do not match any molecules in our databases. Should this occur if we detect emission lines that we cannot identify, speculation will intensify, as this would constitute direct evidence that 3 Atlas is composed of or interacting with something entirely novel. The color changes are more than just aesthetically pleasing visuals. They represent valuable data encoding information about temperature, composition, energy flow, and physical state. Witnessing a comet transition from red to green to blue over a few months signifies a transformation, a progression through different regimes of physics and chemistry. Understanding this transformation by correlating it with known processes or identifying deviations is a primary challenge in studying 3I Atlas. Furthermore, if the comet maintains its blue coloration when it reemerges in November, exhibiting that peculiar azure light weeks after perihelion, it would indicate sustained emission from a source independent of solar distance. This would serve as evidence that whatever mechanism produced the blue color at perihelion remains active, continuing to release energy and distinguishing this object from all others in our catalog of comets. The sequence of red, green, and blue represents 3 colors, 3 states, and three components of a puzzle we are only beginning to assemble. December 19th marks a critical juncture. December 19th, 2025. This is the designated date when the celestial body known as 3I Atlas will achieve its closest proximity to Earth, traversing a distance of 270 million kilometers from our planet. This equates to 1.8 astronomical units. This proximity is sufficiently intimate to permit every significant observatory, both terrestrial and orbital, to scrutinize it concurrently. It is close enough that we will finally acquire the high-resolution imagery, the detailed spectral analyses, and the precise photometric data that will either definitively establish this object as an exceptionally remarkable comet or indicate it to be something entirely different. Lobers frames this particular date as the ultimate adjudication of his theoretical projections. If the detected non-gravitational acceleration during perihelion was indeed a consequence of natural outgassing, akin to the rocket effect generated by sublimating ice, then we should anticipate observing a substantial gaseous envelope surrounding 3 Atlas in December. This would not be a subtle increase or a marginally larger coma than predicted. Rather, it would be a dense, luminous, and unambiguous exosphere of gas, which could only have been formed through the expenditure of 10% of the comet's total mass over a single month. The fundamental principles governing the conservation of momentum necessitate the existence of this cloud if the naturalistic explanation holds true. Conversely, if this cloud is absent, if 3I Atlas presents itself in December with a modest coma, devoid of significant outgassing at its current distance, then the rocket effect cannot have been the source of that propulsion. In such a scenario, the remaining explanations become exceedingly limited and disquieting. Either the estimations of its mass are inaccurate by an order of magnitude, implying that the comet is considerably more massive than currently believed, and thus requires less gas ejection to account for the observed acceleration, or the acceleration itself was not initiated by gas expulsion at all. The mass estimations are derived from observations of its brightness and assumptions about its albedo. Should 3I Atlas possess a significantly darker surface than we surmise, reflecting very little sunlight and obtaining most of its luminosity from its coma rather than its nucleus, then the nucleus itself could be substantially larger. A more considerable nucleus implies greater mass, which in turn necessitates less mass loss to generate a particular acceleration. This proposition is plausible. We have never directly resolved the nucleus. All our estimations of its size are indirect, based on its apparent brightness and our interpretation of that radiance. While we might be mistaken, being incorrect about the mass by the magnitude required to reconcile the figures would imply an implausibly large and implausibly dark nucleus. It would necessitate 3I Atlas being the largest interstellar object ever identified by a considerable margin, possessing a surface that reflects virtually no light, which directly contradicts the spectroscopic evidence indicating the ejection of dust and ice from its surface. There exists a limit to the extent to which parameters can be adjusted before the proposed explanation becomes more improbable than the phenomenon it seeks to elucidate. Consequently, December 19th emerges as a critical juncture. One trajectory leads to a natural comet, exhibiting unusual but ultimately explainable characteristics. The other trajectory leads to a genuine anomaly, demanding novel lines of inquiry, new theoretical frameworks, and perhaps even an acknowledgement that we are encountering an entity that defies our current classifications of astronomical bodies. The observational campaign is already in the planning stages. The Hubble Space Telescope will employ its wide-field camera to capture images of the comet across multiple spectral filters, meticulously measuring its colors and the structure of its coma with a resolution exclusively achievable through space-based imaging. The James Webb Space Telescope will direct its near-infrared spectrograph towards the target, acquiring spectra across wavelengths that are obscured by Earth's atmospheric envelope, thereby identifying molecules invisible to ground-based observatories. Webb's infrared sensitivity will also enable it to ascertain the temperature distribution within the coma, detecting any thermal anomalies or regions where heating exceeds that explicable by simple solar radiation. On the ground, the Gemini telescopes located in Hawaii and Chile will conduct synchronized observations utilizing their adaptive optics systems, striving to attain near-diffraction limited imaging in the near-infrared spectrum. The Very Large Telescope in Chile will deploy its full suite of instruments. Multiple spectrographs will operate simultaneously, covering the ultraviolet, visible, and infrared portions of the electromagnetic spectrum. The Keck Observatory will utilize its cosmic web imager to map the three-dimensional architecture of the coma, visualizing the spatial distribution of gas and dust rather than merely their projection onto the celestial plane. Numerous smaller telescopes will participate in this endeavor. These will include university observatories, amateur astronomers possessing equipment sophisticated enough to contribute meaningful photometric data, and automated survey telescopes capable of acquiring frequent measurements to track changes in brightness hour by hour. The International Asteroid Warning Network, which incorporated 3 Atlas into its observation campaign as a preparatory exercise, will coordinate tracking across multiple sites to ensure uninterrupted coverage. This undertaking is unprecedented. Never before have such extensive resources been allocated to the observation of a solitary comet. The object, Oumuamua, was gone before we could orchestrate such a comprehensive campaign. Borisov garnered considerable attention, but not to this magnitude. 3 Atlas has captured the fascination of the astronomical community in a manner distinct from previous interstellar visitors. This is partly attributable to its inherent anomalies, partly due to the ongoing debate surrounding Lober's theories, and partly because its visibility will extend over several months, affording us ample time for meticulous planning, coordination, and execution of a thorough scientific investigation. The data acquired in December will provide answers to several pivotal questions. Firstly, what is the actual appearance of the nucleus? Can we resolve it? Can we directly ascertain its dimensions instead of inferring them from its luminosity? Hubble possesses the requisite resolution to potentially perceive the nucleus as an extended object rather than a mere point source, particularly if the coma's brightness is not excessively high. If we can accurately measure the nucleus's size, we will immediately establish constraints on its mass, which will subsequently inform us about the magnitude of gas ejection necessary to account for the observed acceleration. Secondly, what is the density of the coma? How much gas and dust are present in the vicinity of the nucleus? This can be quantified through various methodologies. Direct imaging in scattered light reveals dust particles. Spectroscopy, through emission lines whose intensity correlates with the number of molecules present, elucidates the gaseous components. Comparing these two sets of data yields the gas-to-dust ratio, a fundamental characteristic that provides insights into composition and activity levels. If 3I Atlas is characterized by a prodigious coma, an extensive cloud of material surrounding it, this would substantiate the hypothesis of massive outgassing. Conversely, if the coma is of a modest size, comparable to other comets, it would contradict this notion. Thirdly, what molecules are present and in what proportions? The spectroscopic observations will identify emission lines, measure their precise wavelengths and intensities, and compare them with established laboratory data and theoretical models. We will ascertain whether carbon chains are present in quantities sufficient to explain its characteristic green hue. We will determine whether the blue emission originates from carbon monoxide ions or from an alternative source. We will identify the presence of unexpected molecules, chemical species that should either be absent or present in negligible amounts, hinting at unusual formation conditions or intrinsic chemical processes. Fourthly, is there any discernible structural organization within the coma, such as jets, streamers, shells, or asymmetries? Active comets frequently exhibit jets of gas erupting from specific points on the nucleus, creating intricate patterns within the coma that offer clues about the nucleus's rotation and the distribution of active regions. If 3I Atlas displays prominent jets, if the emission exhibits significant asymmetry, this could provide a natural explanation for the non-gravitational acceleration as a direct outcome of uneven outgassing. Conversely, if the coma appears symmetrical, devoid of any clear jet structures, this renders the acceleration more challenging to explain through conventional cometary physics. And fifthly, has the color been sustained? Will 3I Atlas retain its blue coloration in December, or will it revert to a red, green, or white hue? The evolution of its color constitutes one of the most diagnostically significant pieces of information, as it directly informs us about the energy source driving these changes. If the blue color proved to be transient, induced by specific conditions experienced at perihelion that are no longer applicable, then it was likely a natural yet atypical phase transition. However, if the blue color persists, if the comet remains anomalously blue, even at a distance of 1.8 astronomical units from the Sun, this would suggest an ongoing emission process requiring further explanation. The temporal aspect of the observations is of critical importance. December 19th marks the closest approach, yet 3I Atlas will remain advantageously positioned for observation throughout December and into January. The comet will be visible in the pre-dawn sky, ascending before sunrise, observable for several hours before twilight renders observations impractical. The lunar phase proves cooperative. A new moon occurs in mid-December, providing a period of dark skies precisely when they are most needed. By late December, the moon will have returned, but the comet will be sufficiently luminous and elevated that lunar interference will not entirely preclude observation. Multiple observations conducted over several weeks will allow us to detect changes. If the comet is diminishing in brightness rapidly, losing luminosity at a rate exceeding predictions based solely on distance, this would suggest that the outburst at perihelion was a temporary event, and the activity level is reverting to its baseline. If the brightness remains constant or decreases slowly, this would indicate sustained activity, either from continuous sublimation or from some internal process that is not contingent upon solar heating. Time series data consistently offers greater insight than isolated snapshots, as it elucidates dynamics, evolutionary trends, and patterns that point towards underlying mechanisms. Furthermore, there exists the potential for unforeseen discoveries. 3I Atlas has already presented us with multiple surprises. It astonished us with its premature outgassing. It surprised us with its emission of nickel. It astonished us with its rapid increase in brightness. It surprised us with its distinctive blue color. Each time we believe we have grasped its nature, each time we construct a model that accounts for the existing data, new observations emerge that do not perfectly align. December may very well bring further surprises. The coma might exhibit features that no one anticipated. The spectrum could reveal emission lines from molecules that were entirely unexpected. The nucleus's appearance might deviate from what our models suggested. Lowe has stated that if the substantial gas cloud is absent, thereby falsifying his prediction, it would serve as evidence that the rocket effect is not responsible for the observed acceleration, necessitating the invocation of an alternative explanation. However, he has also tempered this assertion, noting the uncertainties in mass estimations, the possibility that the required gas cloud might be fainter than anticipated, and the principle that the absence of evidence does not invariably constitute evidence of absence. This represents sound scientific practice. Predictions should be empirically verifiable but not so rigidly defined that a single observation can definitively confirm or refute them. Reality invariably exceeds the complexity of our theoretical constructs. Interpretation is perpetually required. The prevailing scientific community, which differs in opinion from Lowe, is equally invested in the December observations. They anticipate observing a comet, an active entity that outgasses and sublimates, possessing a composition that is unusual yet comprehensible. They expect the spectrum to exhibit the molecules we have already identified, perhaps with the addition of a few more. They anticipate its brightness and color to be consistent with natural processes, possibly necessitating minor refinements to existing models, but nothing revolutionary. They expect 3I Atlas to conform to the established framework for interstellar comets, even if it occupies a niche within that framework where no other object currently resides. Both factions will acquire data. Both factions will conduct analyses. Both factions will publish their findings. And both factions will engage in debate regarding the interpretations, as this is the inherent nature of scientific progress. Consensus emerges gradually when phenomena are subject to ambiguity. However, December will, at the very least, narrow down the range of possibilities. It will provide us with concrete data where currently we have speculation. It will supplant theoretical models with empirical measurements. And this transition from uncertainty toward knowledge, however incremental, however incomplete, is precisely what imbues the observation campaign with its profound significance. 1 month, one closest approach, one unparalleled opportunity to observe 3I Atlas from the optimal vantage point attainable. Subsequently, it will continue its journey, receding into the cosmic darkness, leaving us to decipher the meaning of what we have witnessed. Physicist Brian Cox aptly characterized it as a message from a dead world. This is not in the sense of extraterrestrial communication or manufactured artifacts, but rather in the deeper, more poignant implication that 3 Atlas is a remnant of something that no longer exists. The star system from which it originated, the planetary disk where it coalesced from ice, dust, and organic molecules, the gravitational forces that ultimately propelled it into interstellar space, all of these events transpired billions of years ago. The world that engendered 3 Atlas has vanished, transformed beyond recognition. Perhaps its parent star has evolved beyond the main sequence. Perhaps its constituent planets have migrated or been annihilated. It is conceivable that nothing remains of the original system except this solitary icy traveler drifting through the galaxy, carrying the chemical imprint of a place and time forever beyond our reach. This perspective is inherently humbling, irrespective of whether 3 Atlas is classified as a comet or something more profound. It serves as a potent reminder that we inhabit a universe where much of existence remains inaccessible to us, where most of history has already unfolded, leaving behind only faint vestiges, and where the celestial bodies we study are often the last survivors of processes that concluded eons in the past. 3 Atlas has been in transit for an estimated period ranging between 3 billion and 11 billion years. It has passively witnessed the galaxy's evolution in ways that transcend our comprehension. It has traversed regions of space that we will never reach. And now, by sheer coincidence, its trajectory has intersected with ours for a span of several months. If it is a natural comet, if all its observed anomalies can be resolved into unusual yet comprehensible physical and chemical phenomena, then 3I Atlas continues to impart profound knowledge. It demonstrates that comets originating from other star systems can exhibit characteristics radically divergent from those found within our own solar system. It illustrates that the formation conditions surrounding other stars, the chemical compositions of their planetary disks, and the processes that shape and age interstellar ice over cosmic timescales all contribute to a diversity that we have only begun to explore. Each interstellar object serves as a data point reflecting the galaxy as a whole. Every observation of these infrequent visitors expands our understanding of the potential, the commonplace, and the peculiar aspects of the cosmos beyond our immediate celestial vicinity. The age estimates are particularly striking, around 7.5 billion years. This predates our solar system by more than 50%. The Sun did not exist when 3I Atlas was formed, neither did Earth. Life itself was not yet present. The galaxy presented a different aspect, with a greater abundance of young stars, more vigorous star formation, and a different distribution of metals and heavier elements. Whatever star system gave rise to 3 Atlas was part of an earlier stellar generation, composed of material that had undergone fewer cycles of stellar birth and death. Its chemistry should reflect this ancient origin. Its isotopic ratios should differ. The abundances of trace elements should narrate a story of nucleosynthesis processes that occurred billions of years prior to the inception of our own solar system. This is precisely why spectroscopy assumes such paramount importance. We are not merely measuring the present molecular composition as the comet undergoes sublimation. Rather, we are ascertaining the elements that were extant in that ancient star system, the conditions that prevailed in its outer regions where volatiles could condense, and the type of radiation and cosmic ray environment the nucleus encountered during its interstellar voyage. Every emission line, every isotopic ratio, every molecular abundance constitutes a clue pertaining to the history encoded within this object. If the observed dominance of carbon dioxide is indeed accurate, if 3 Atlas is composed of 87% carbon dioxide by mass, this would provide insights into the temperature and pressure regimes of the disk where it originated. Carbon dioxide preferentially condenses in extremely frigid environments, colder than the regions where the majority of solar system comets formed. This suggests that 3I Atlas originated far from its parent star, possibly within or beyond what we recognize as the Oort cloud. It was born in extreme cold and has remained so ever since, never venturing sufficiently close to a star to shed its volatile ices until this present moment. The signature of nickel without iron, if it persists in December observations, points towards chemical processes that we do not fully comprehend. Natural astrophysical phenomena invariably produce nickel and iron in conjunction, as they are synthesized together during supernova events. Both are elements of the iron group with similar properties. They condense together in stellar outflows and should therefore be inseparable. Yet, 3I Atlas is emitting nickel prominently while iron remains undetected. This could signify that the formation environment possessed peculiar conditions, a chemistry that selectively incorporated nickel over iron. Alternatively, it might imply that the nucleus has undergone some form of processing, altered by a mechanism that segregated the two elements. A third possibility is that we are observing an industrial signature, the result of refining processes that do not occur naturally. This latter possibility is what keeps Lober's hypothesis in contention and prevents mainstream astronomers from entirely dismissing his arguments. Because even if the probability is low, even if every instinct suggests a natural origin, the nickel signature presents a genuine enigma. When this is considered in conjunction with the other 8 anomalies, when the entire suite of properties is examined rather than any single characteristic in isolation, the cumulative weight of evidence becomes compelling. It begins to feel as though something must yield, as though our established models require extensive revision beyond comfort, and as though we are compelled to accept an excessive number of coincidences. The trajectory of 3I Atlas through our solar system represents another crucial element of this complex puzzle. It is projected to pass in proximity to Venus in early November of 2025, having already passed near Mars in October. Subsequently, it will approach Jupiter in March of 2026. Its orbital path traverses the plane containing all significant celestial objects, and thus all potential targets for observation or interaction reside within this region. If one were tasked with designing a mission to survey a star system, aiming to visit multiple planets within a single transit, this would be the precise trajectory to select. Alignment with the ecliptic would be prioritized, its perihelion timed to coincide with opportune planetary positions, thereby maximizing the scientific return from such a flyby. Naturally, celestial bodies can also follow such trajectories. Comets originating from the Oort cloud occasionally enter ecliptic-aligned orbits purely by chance. While the probability is low, it is not zero. Moreover, having observed a sufficient number of comets over centuries, it is statistically inevitable that even unlikely cases will eventually manifest. 3 Atlas might simply represent one of these infrequent occurrences, a natural object whose trajectory appears optimized due to a fortuitous geometric alignment. However, it is prudent to consider what we would observe if an interstellar probe were to visit our solar system. What indicators might betray its artificial nature? What observations would distinguish it from a naturally occurring comet? Lober's contention is that most of the anomalies exhibited by 3 Atlas align precisely with what would be anticipated from a technologically advanced object. The orbital alignment, its unusual composition, the observed acceleration in the absence of visible outgassing, its considerable speed and size, and its meticulously timed trajectory. If all these characteristics were observed in a human-made spacecraft, we would unequivocally recognize it as artificial. We grant it a pass as a natural phenomenon solely because we presume the alternative is too improbable to warrant serious consideration. This presumption may well be erroneous. We possess no definitive knowledge regarding the prevalence of technological civilizations within the galaxy. We have no certainty concerning the number of such civilizations that might have constructed interstellar probes. We are unaware of what proportion of these probes might traverse our solar system within any given century. The number could be 0, it could be minuscule, or in a galaxy of considerable age and high stellar density, it could be sufficiently substantial that encountering one within a human lifespan is not an implausible event. We simply do not know. In the absence of definitive knowledge, we default to skepticism, adopting the assumption that the universe is predominantly natural and technology is exceptionally rare. However, this assumption remains merely an assumption. This is not founded on tangible proof. Instead, it relies on preconceptions, on what appears sensible considering our confined observations. 3 Atlas is challenging these established notions. It's probing our willingness to revise our perspectives when confronted with unusual occurrences. It questions if we're receptive to possibilities that seem improbable but can't be definitively dismissed. It asks if we can contemplate multiple explanations concurrently without settling too quickly on the one that offers the most comfort. The observations scheduled for December will be instrumental. They will yield data that limits the range of possibilities, rendering some interpretations more likely and others less so. However, they will not provide absolute certainty. They will not conclusively prove whether 3 Atlas is a natural phenomenon or an artificial construct. They will influence our understanding, alter the statistical likelihoods, and furnish us with more information to process. And that is the extent of what scientific inquiry can truly achieve when grappling with singular, ambiguous phenomena that resist easy categorization within existing paradigms. In March of the year 2026, 3I Atlas is slated to traverse near Jupiter. The Juno spacecraft currently orbiting the gas giant may have the capability to observe the comet from an additional perspective. Europa Clipper, should it have reached the Jovian system by that juncture, could contribute its sophisticated instruments to this endeavor. These forthcoming observations will represent our final substantial examination before 3i Atlas departs the solar system entirely, embarking on its return journey into the interstellar medium from whence it originated, after which it will be irrevocably gone. It will become another celestial body in our records, another publication in scientific journals, another protracted discussion that never reached a definitive conclusion due to insufficient evidence and the ephemeral nature of the phenomenon. Unless something extraordinary transpires, unless the December observations unveil something so utterly aberrant, so demonstrably outside the realm of natural behavior, that even the most hardened skeptics are compelled to concede we are witnessing something remarkable. Such is both our aspiration and our apprehension. The hope is that we might be privy to something genuinely unprecedented, something that broadens our comprehension of the universe's contents. The fear is that we might discover we are not solitary, that other sentient entities exist, and that we have been too myopic or overly hesitant to recognize the indicators when they manifested in our telescopes. Regardless of the outcome, 3i Atlas has already succeeded in prompting us to scrutinize our fundamental assumptions. It has catalyzed dialogues that would otherwise have remained dormant. It has compelled scientists to articulate the basis of their convictions, to substantiate their positions with empirical data rather than mere pronouncements of authority, and to engage with challenging concepts rather than outright rejection. Furthermore, it has served as a potent reminder that the cosmos is replete with enigmas. It has underscored that our exploration has encompassed merely an infinitesimal portion of existence. It highlights that every novel object, every perplexing observation, every anomaly that eludes straightforward explanation presents an invaluable opportunity to acquire knowledge previously unknown to us. Whether 3i Atlas is a remnant from a defunct world or something more profound, it is imparting a lesson, and we ought to be appreciative of this educational experience, irrespective of its eventual resolution. The ancient ice holds memories. It preserves records of a temporal and spatial context inaccessible to us, of physical and chemical processes, and perhaps even of the aspirations of beings we have never encountered. Our role is confined to observation, measurement, analysis, and the diligent effort to decipher the message embedded within those frozen molecules, hurtling through the void at 61 kilometers per second. A communication from a long-vanished world, or a harbinger from a living one. The month of December will bring us nearer to that revelation.